Welcome back to the course on Introduction to Material Science and Engineering offered by EdupediaWorld. Previous couple of lectures we saw how to find out the crystallographic directions, and if the crystallographic direction is given for a particular direction, then how to find the Miller indices for the same. Now next we would like to see how to find different planes in a particular crystal. What is the identity of different kind of planes? If the Miller indices are given, how do we find the corresponding plane? If a plane is given, how do we find the corresponding Miller indices? So let's start with that topic. Similar to crystallographic directions, crystallographic planes are also based on the unit cell and the three coordinate system of the unit cell. We base the Miller indices which we find based on that coordinate system. Now for the cubic system, we use the 3 Miller index system similar to the direction, and for the hexagonal system we use the 4 Miller index system, again similar to hexagonal direction. One point to note here is if you remember, for the direction we used this bracket. For planes we use this bracket. This is a notable difference. This is the convention. So whenever you see something like 1 2 3, this means direction 1 2 3. Whenever you see something like 1 2 3, this means plane 1 2 3. So do not mix them up. And interesting feature about crystallographic planes is if two planes have same Miller indices, then they are parallel to each other. Put the other way around, if two planes are parallel to each other, they will have same Miller indices. Okay, now let us see how exactly do we find Miller indices. Before that, a couple of notes. One is that I have just said that a particular plane is represented by this bracket, right? But if we are representing a family of planes, we use this bracket instead. Similarly, for the direction case, it was this for a particular direction and this for a family of direction, right? These are parallel concepts. Then again, in a cubic system, if we have a plane and direction such that direction is, let's say, 1 0 0, and the plane is also 1 0 0, then for a cubic system, without doubt you can say that this direction is perpendicular to this plane. It is always true. This is the result of geometry. So this won't ever collapse. This will always hold true. Okay, with this short notes, let's get back to how do we find Miller indices for a plane. Note that we are discussing about the cubic system for the time being. So suppose you are provided with a particular plane, okay, and if that plane whose Miller indices you need to find passes through the origin, then you need to do either of these two tasks. Either you can shift the plane parallel to the original plane. As I said in the previous slide, that parallel planes have same Miller indices, so it does not matter if you shift a plane parallel to itself. The main idea is that the plane should not pass through the origin. So to avoid it from passing through the origin, you can either shift it from parallel to the original plane. Alternatively, what you can do, you can choose a different origin. So you can shift the origin itself so that the existing plane no longer passes through the origin. So this is the first step. Visualize the plane. If it passes through the origin, shift the plane or shift the origin. Next, what you do is note the lengths at which the plane cuts the three axes. As I have said, there will be three axes corresponding to the three coordinate axes, and the plane will cut the three axes somewhere, right? You need to note what is the length at which they cut the axis. Suppose it does not cut one of the axes. That means it cuts the axis at infinity length. So you take infinity as the length. Third step, what you do, you take the reciprocal of the lengths which you got, of the three lengths. Okay, now once you take the reciprocal of the three lengths, it may turn out that one or more length is no longer an integer. If it so happens, then what you do is that you multiply all the three with a common value such that all of them turns into a possible integer, and the possible integer should be the smallest integer possible, right? Finally, now this values which we got after multiplying with a common number are the three Miller indices of the plane, and this is expressed as HKL. So this is my Miller indices for that particular plane. Now this is the basic algorithm which should be used to find Miller indices of a given plane. Rather, if you have the Miller indices, we backtrack the process and find the plane. Now let us see some examples to concrete the idea and to make it much more clear. Fine. This example I will discuss for the cubic system. These four planes will try to plot. So as I said, the coordinate system which I will follow is the same as I used in the crystallographic direction case: X, Y, Z. So this is my Y direction, X and Z. Let's first try out 1, 0, 0. 1, 0, 0 Miller indices means in order to find where it will cut the three axes, you need to take the reciprocal of this, right? So for 1, 0, 0, the reciprocal will be, you take the reciprocal, you get 1, infinity, infinity. That means that the plane which we are looking for will cut x-axis at 1 unit. So over here it will cut y-axis at infinity, so it will be parallel to y-axis, and it will cut z-axis at infinity too, so it will be parallel to z-axis too. That means the plane should be like this, in this direction parallel to z-axis, and in this direction parallel to y-axis, and it should cut x-axis at 1 unit. Therefore the plane which we are talking about is actually this particular plane, this face of the cube. Now that we have the face of the cube, let's see if it is actually what we were looking for. Okay, now back to the algorithm. This does not pass through the origin. This is the origin, so it does not pass through the origin. Where does it cut x-axis? It cuts x-axis at 1. Where does it cut y-axis? At infinity. Where does it cut z-axis? Again at infinity. Now we take the reciprocal of this and we get 1, 0, 0. So that is indeed the plane which we are looking for. Similarly, let us see 0, 1, 0. 0, 1, 0 means x-axis at 0, at infinity. So it will be parallel to x-axis, this. Y-axis at 1, right? So y-axis at 1, y-axis at 1 parallel to x-axis and parallel to z-axis too, right? Parallel to z-axis too. So the plane which we are talking about is this. This was 1, 0, 0. This is 0, 1, 0. Similarly, if we talk about 0, 0, 1, x and y will be cut at infinity and z will be cut at 1. So z will be cut at 1 over here, and x and y at infinity, so parallel to this and parallel to this. Thereby we get this particular face of the cube as 0, 0, 1. Okay, so this particular face is 0, 0, 1. So now you see how we get the required plane from the Miller indices. Now let us try a little different case. The case we'll look into now has 1 1 1. So 1 1 1, if we take the reciprocal, we get the same 1 1 1. That means this particular plane which we are looking for cuts x, y and z each of the axis at 1. So it should cut here, it should cut z here and y here. Therefore the plane which we are looking for is something like this. If we join these 2 points, if we join, sorry, it should be a straight line, this 2 point, and if we join this 2 point, then the plane which we get something like this, which will have, it's inclined to all the 3 axes, therefore it cuts all the 3 axes, right? This plane is 1 1 1 plane which we required. Okay, now let's move to some more practice. Over here we are asked to find 0 bar 1 1. This is x, this is y, and this is z axis. Now I need 0 bar 1 1. So what I do, I take the reciprocal, I get infinity bar 1 1. So x axis will be cut at infinity, so it's basically parallel to x axis. I'll let it be there. Then we go -1 unit in the y axis. So if we extrapolate this to another cube, then the -1 unit will be somewhere around here, right? -1 unit. And the z axis we cut at 1 unit, right? So the plane should be something like this, right? But it should also be parallel to x-axis, isn't it? Therefore what will happen is this line which we draw is parallel to x-axis, thereby this will be my line, and what is happening is this is basically this point extrapolated here. So this is the plane which we are looking for. 0 bar 1 1. Let us try to figure out if it is the correct plane. How do we figure out? 0 means parallel to x-axis. Obviously it is not cutting x-axis anywhere. X-axis goes here, it extends till infinity without cutting it. Bar 1 means 1 unit negative y, so it cuts y-axis at -1 indeed, and z-axis at +1. It cuts here the z-axis at +1. So we have got the plane which we are looking for. This is that plane. Now let us try one little more complicated case. The complicated case that we are going to look is 1 2 3. Okay, 1 2 3. So what do we do first? We take the reciprocal to find the distances at which it will cut the x, y and z axis. So the reciprocals will be 1 half 1 by 3. Therefore this particular plane which we are looking for will cut x-axis at 1, y-axis at half, so somewhere around here, and z-axis at 1 by 3rd, positive 1 by 3rd, right? And this is my origin, so z-axis over here. Therefore the plane which we'll get will be something like this. Okay, so this is the plane which we were looking for. This is 1 2 3, plane 1 2 3. Fine. So these few examples must have given you a glimpse about how to find a given plane provided you are given the Miller indices. Now let us see a couple of examples where we are given a plane and we are asked to find what is the Miller index for that plane. So let us suppose that I have a plane like this. This is a hypothetical example. You can draw any plane and find the Miller indices for it. Okay, this is half length and this is obviously one length, and this is not cutting Z anywhere. Let me draw the axis Y, X, Z. So now using the algorithm, we need to find this plane. What are the Miller indices of this plane? So first you need to find whether it is passing through the origin. Okay, it is not passing through the origin, so this plane itself will do the task. Now where does it cut the x-axis? It cuts the x-axis at 1 unit length. Where does it cut y-axis? It cuts y-axis at half unit length. And z-axis, it cuts at infinity. It's parallel to z-axis, so infinity. Now we take the reciprocal. We take the reciprocal 1, 2, 0. This is all three in integer, so we can directly write the plane's Miller indices are 1, 2, 0. So we have got the Miller index for this plane as 1, 2, 0. This is the simple algorithm. Let us just try one more example. Let me say, okay, let's do it like this. Let's say we have a plane like this at half itself, okay, and this is actually a straight line. So the plane which I am looking for is this plane. So it's cutting here at half, y-axis at half everywhere, which means that it is parallel to x-axis and it is parallel to z-axis also, but it's cutting y-axis at half. So x will be 0 since it is parallel to rather infinity since it is cutting x-axis at infinity. Y will be equal to half and z will be again equal to infinity because it's not cutting anywhere, it will be cutting at infinity. When I mean that z is cutting at infinity, that means it is parallel to z-axis. It never actually cuts it. That's why infinity. Okay. Now we take the reciprocal of this. So it turns out to be 0, 2, 0. Okay. So this plane, you can say that this is 0, 2, 0 plane. But note that here we have not reduced it into the smallest possible integer. We do that and what we get is 0, 1, 0. So this plane turns out to be 0, 1, 0. Right? But a couple of slides back we saw that 0, 1, 0 is this plane, right? This top plane. So how come this is also 0, 1, 0 and this is also 0, 1, 0? The matter of the fact is, as I said in the initial slide, that all parallel planes will have same Miller indices. Therefore, this plane and this plane being parallel has same Miller indices. In fact, even this plane, the base plane, is also 0, 1, 0. Any plane parallel to z-axis and x-axis is 0, 1, 0. Okay? Hope this gives you a lot of insight into how to find the crystallographic plane and corresponding Miller indices for a cubic system. Now let us see two examples for the body-centered and face-centered case. The body-centered, we know that the closed packed direction was this direction, right? Passing through the body-centered. Similarly, the closed packed plane for body-centered is this. The plane which passes through the corners as well as the body center. Okay. So now if I ask what is the closed packed plane for a body-centered cubic, how do we find it? X, Y, Z. So where does it cut x-axis? At 1, Where does it cut y-axis? Again at 1. Where does it cut z-axis? At infinity. Reciprocal 1, 1, 0. So this particular plane which we are talking about is 1, 1, 0. That is our closed packed plane for body centered. But in fact, this is not the only closed packed plane. If you take, let's take a different color. If you suppose this plane, right? It's difficult to visualize, but I will try. If you suppose you take this plane, right, then in fact this plane is also a closed packed plane because it passes through these 4 corners and through the body centered. So if this were the plane which we are looking for, then what would have been the Miller indices for this? Now if we take this as the origin, then it passes through the origin, this plane. So we need to shift the origin. Let's take this as the origin. So now this is y, this is x, and this is z. X, y, z. Where does it cut x-axis? It cuts x-axis at -1. -1. Where does it cut y-axis? At +1. Where does it cut z-axis? It is parallel to z-axis, so 0. Right? Take the reciprocal. Again bar 1, 1, 0. So this plane which we have got here is bar 1, 1, 0. So basically what you can see is closed packed planes for a body centered cubic system is the family of planes 1, 1, 0. This includes 1, 1, 0, 1 bar 1, 1, 0, 1, 0, 1, all those kind of plane. Okay. Next, let us see for the face centered. The closed packed plane. The closed packed direction was this direction, right? The closed packed plane will be one in which the 3 face centers will lie. So this will be my closed packed plane. Where does it cut? If this is y, x and z, it cuts x at 1, y at 1 and z at 1. Take reciprocal 1, 1, 1. So the plane, closed packed plane for FCC is 1, 1, 1. There are similar closed packed planes which will lie in the family of 1, 1, 1 itself. You can try that as an example for your own sake. Fine. Now that we have seen the crystallographic planes for cubic system, let us see crystallographic planes for hexagonal. Similar to the direction case, here too, instead of 3 Miller indices, what we do is that we use 4 Miller indices. Instead of HKL, we use HK, I and L. Again, following the same condition, H plus K plus I is equal to 0. I is effectively redundant because of this condition, but we use I because it helps visualize 2 planes which belong to the same family. Let's see this case, right? If we have to draw 1, 0, 0 plane for hexagonal, or alternatively this will be 1, 0 bar 1, 0, right? Because this plus this plus this should be 0. Then which plane will be this? Drawing plane from Miller indices is quite simple for hexagonal. What you do is you go as per this is A1, this is A2. So you go 1 unit in A1 direction and parallel to A2, right? Parallel to A2. And in the third direction, that is C direction, also parallel to C. Therefore, we have to be parallel to C axis, we have to be parallel to A2 axis. And A1 is over here, we are at 1 unit. And we already see that A3 itself turns out to be -1 unit. So basically over here. Therefore, the effective plane which we are getting is this already shaded plane, right? This is the plane that we actually needed. This is 1 0 bar 1 0. Now let us see bar 1 0 1 0. So A1 unit will be -1. So instead of coming 1 unit over here, we go 1 unit backwards. This, okay. A2 is 0, so again parallel to A2, so this will be my line. A3, automatically it intersects here, so A3 is 1, and C axis again 0, that means C axis will be cut at infinity, so parallel to this axis, thereby the plane which we are looking for is this plane back here, this face of the hexagonal system. This face is bar 1 0 1 0. Fine. Now one example, let's see. These are, let's do it in a different diagram. These are the basal plane. Okay, these are known as the basal plane. This is the base. So let's suppose we want to find what is the Miller indices for this plane. Okay, so what we have to do is that we have to find A1, A2, A3 will automatically turn up, and C. Where does it cut each of them? It cuts A1, this plane cuts A1 at infinity. It cuts A2 at infinity as well. Thereby A3 is also cut at infinity, and C will be effectively 1 unit, right? So 1 unit. We take the reciprocal, we get 0 0 0 1. Therefore the Miller indices for this particular plane is 0 0 0 1. And similar to the cubic system, here too all the parallel planes will be having same Miller indices. So whether we are looking at this plane or we are looking at the actual base plane, both are 0 0 0 1. Why cannot we do directly from here? Because here this is my origin, it's lying on the origin, so we parallelly shift it here and find it as 0 0 0 1. Fine. Now let us just try one more example. Let's take let's do this plane, right? This face plane, this front face. So for this front face, what is happening is this is the origin, right? For the front face is cutting A1 at 1 unit, isn't it? Here it is cutting 1 unit. It is cutting A2 at -1 unit. This is positive A2, so it is cutting A2 at -1 unit, bar 1 unit. It's cutting A3 at infinity. It is parallel to A3, infinity. Okay, and it is cutting C at infinity also. It's parallel to C also. We take the reciprocal, we get 1 bar 1 0 0. So this plane which we were talking about is 1 bar 1 0 0. Fine. 1 bar 1 0 0. So this brings us to a conclusion about crystallographic plane. Last couple of lectures we studied crystallographic directions. I understand that this is a bit this might appear a bit tricky, so the catch here is to practice 3-4 sets of planes and direction on your own, both for the cubic system and the hexagonal system, to get a hold of how exactly the process is taking place. Hopefully this lecture helped you. In the next lecture, what we'll do is we'll study about isotropy, anisotropy, single crystal, polycrystal, those kind of things. So till the next lecture, have a great day. Goodbye.